Today we're going to look at a type of elliptic curve known as a Mordell curve. And we're also going to look at some examples when there are or are not integer points on these curves. Okay, so let's look at what a Mordell curve is. Well, at least one special type of curve like this is of the form y squared equals x cubed plus n, where n is an integer. Now, the shape of these curves will obviously depend a bit on the value of n, but they all have the general shape that looks like this graph over here. And now, maybe a classic question to ask is, when are there integer points on these curves? And the answer to that is, sometimes, but there are only ever finitely many integer points on these curves. Now what I'd like to do is look at some examples, two examples when there are not solutions, and one example where there is a solution. So let's start with this case when n is equal to 7, and we'll show that the curve y squared equals x cubed plus 7 has no integer solutions. And the idea here is to break this into three cases. And these cases will be, well, kind of based around the fact or the setup of having even values of x or odd values of x. But we'll look at two different types of odd values of x. Okay, so our first case will be the case when x is even. So that means we can write x as 2 times a. But observe, that tells us that y squared is equal to 8 times a cubed plus 7. Now the trick that we use now is to reduce mod 4, and this is like a fairly standard trick whenever you're showing that something doesn't have a solution. Okay, so reducing mod 4, we'll get y squared is congruent to 3 mod 4. And that's because 8 is a multiple of 4. That means it's 0 mod 4, whereas 7 is 3 more than a multiple of 4. But this may not seem like much of a problem, but it in fact is. Because if we were to make a chart of the perfect squares mod 4, which maybe we should have on the board just for good measure, we'll see that we never achieve the number 3. So notice that 0 squared is 0, 1 squared is 1, 2 squared is 4, but 4 is 0 mod 4, and then 3 squared is 9, but that's 1 more than 8, so that's 1 mod 4. So what we see here is we never achieve the number 3, so this tells us that there is no solution. Because if we had a solution, then we would have a square root of 3 mod 4, which we clearly don't. Okay, so now let's move on to the second case, which is the first of our two odd cases which we'll investigate. And this is the case when x is equal to 4a plus 3. So all odd numbers are either of the form 4a plus 1 or 4a plus 3, and here we're going to look at 4a plus 3 first. Okay, but that means that we have y squared is equal to 4a plus 3 quantity cubed plus 7. But now we're going to reduce this thing modulo 4 again. So that's going to give us 3 cubed, but I'm going to write 3 as -1. So we've got -1 cubed. And then 7 is equal to 3. We've got -1 cubed plus 3, but -1 is clearly equal to +1. So here we'll get that y squared is congruent to 2 modulo 4. But again, we run into the same kind of problem that we did before. Just looking at our chart, we'll see that 2 is not a perfect square mod 4. So that means here we also have no solution. Okay, so the first case did not give us a possibility. The second case also did not give us a possibility. So that means we should probably move on to the third case. And that third case will be the case when x is equal to 4a plus 1. Okay, but now let's observe that we've got y squared is now equal to 4a plus 1 quantity cubed, and then plus 7. But I'm going to take that plus 7 and write it as plus 8 minus 1. But now observe that right here, these first two terms represent a sum of cubes. But there's a nice factorization formula for sums of cubes. And so that's gonna factor like 4a plus 1 plus 2 times something. And you can write what that something down is if you want to, but it doesn't really matter. And then we'll have minus 1 here. Oh, but then this is going to be equal to 4a plus 3 quantity cubed times some number, which I said it doesn't really matter what it is, minus 1. And now here's the trick. Any number that's of the form 4a plus 3 has a prime that's of the form 4n plus 3 or congruent to 3 mod 4 that divides it. So that's a standard rule from number theory. So let's take that prime. So let's let p, which is congruent to 3 mod 4, be such that p divides 4a plus 3. And then let's reduce this whole equation mod p, starting over there here on this side, which is y squared, and then over here. Okay, so that's going to give us the following congruence. Y squared is congruent to -1 mod p, because that 4a plus 3 is a multiple of p by like the setup that we built into this. Oh, but -1 is not a perfect square mod primes that are congruent to 3 mod 4. That's another fact from number theory. We can actually prove that. So let's suppose that this solution was satisfied. Okay, but if that solution was satisfied, then the order of y would be equal to 4 inside of the group of units modulo p, which is called UP. But then let's recall that order of an element always divides the order of a group. But that means that 4 divides the order of the group of units mod p, which is p minus 1. But if 4 divides p minus 1, then p must be congruent to 1 mod 4, but that's a contradiction. So that gives us a contradiction. So that means this case also does not give us a solution. So case 1, 2, and 3 don't give us a solution. That means we have no solutions at all. Now let's move on to another example. So our next solution is worked out in detail in some lecture notes by Keith Conrad from the University of Connecticut. So you can check, his solution to this, which is pretty similar to ours, as well as a bunch of other examples if you go to his website. Okay, so we'll now show that y squared equals x cubed minus 24 has no solutions. Okay, so the way to do this is to somehow get either a sum of cubes or a difference of cubes over on the right-hand side. And we'll do it by writing y squared plus 16 equals x cubed minus 8. So there, we've got a difference of cubes over there on the right. But now we can factor that right-hand side, so x minus 1, x squared, and then let's see, it'll be plus 2x plus 4. But now I'm going to write this as x minus 2, and then we'll have x plus 1 squared plus 3. And now that we have this set up, we're ready to go into our cases. And we'll use, well, not exactly the same cases that we did last time. We won't need quite as many. We'll simply need an odd case and an even case. So our first case is if x is odd, which means I can write x as 2 times a minus 1. Okay, but then let's plug that into our equation. We have y squared plus 16 equals, so we're going to have some number, which is the x plus or x minus 2 part. And then over here, we're going to have 4a squared plus 3. But notice that this thing has a factor that's of the form 4 times something plus 3. So we can do the same kind of thing that we did before. Let's go over here and let's let p, which is congruent to 3 mod 4, be a divisor of this number, just like we did in the last example. And now let's reduce this whole thing mod p again. So that's going to give us y squared plus 16 is congruent to 0 modulo p. Okay, nice. But now that's going to give us y squared is congruent to negative 4 squared mod p. But now p is a prime that's congruent to 3 mod 4. That means 4 has a multiplicative inverse modulo p. So let's multiply both sides of this congruence by the multiplicative inverse of 4 squared. So that's going to give us something like this. So I'll write that as 4 inverse times y all squared is congruent to minus 1 mod p. But here we've got the same problem that we did before. Minus 1 is another perfect square mod a prime that's not allowed to have a perfect square by our previous discussion. So that leads us to a contradiction, which means it's impossible up here for x to be odd, which means we must have the case when x is even. So now let's look at that case on its own. So far we've gotten to the point where we showed that x must be even, but then that means we can write it as 2 times a. But just really quickly looking, that means the right-hand side of this equation is a multiple of 8, which means y squared is a multiple of 8, but that means that y, well, you might say that it's just even, but it actually has to be a multiple of 4. So that means we can write y as 4 times b. Okay, so now plugging that into our original equation, we'll have 16 times b squared equals 8 times a cubed minus 24. But from here what we can do is divide this entire equation by 8. So that'll give us 2 times b squared equals a cubed minus 3. So let's put a box around that, because at this point all we have to do is consider this new auxiliary equation. Okay, so next up what I'm going to do is manipulate this a little bit. Let's write this thing as 2 times b squared plus 4 equals a cubed plus 1. And the reason I want to do that is to get a difference, or I should say a sum of cubes on the right-hand side. Now let's write this as a plus 1 times a squared minus a plus 1. But now let's observe that a squared and a have the same parity. That means their sum and difference is always even. But that means when we add 1, we most definitely get an odd number. So this thing is odd. Furthermore, it's fairly easy to show or to check that not only is it odd, but it's bigger than 1. Notice if it's equal to 1, then a is 0. But if a is 0, then x is 0. But then if x is 0, y squared is negative 24. But that's clearly not a solution. So like I said, this is odd and, well, bigger than 1, which means it's bigger than or equal to 3. Now what we'll do is take an odd prime factor of this, and we'll call that prime factor p. And now we're going to reduce this whole thing modulo p. So I think you could probably see the theme here is that we create a prime factor of a certain type, and then we reduce that mod prime factor and then show that something bad happens. That's exactly what's going to happen here. So we have 2b squared plus 4 is congruent to 0 modulo p. But then putting some things together here, we'll eventually see that b squared is congruent to negative 2 mod p. So that's simply by subtracting 4 from both sides of the congruence and dividing by 2. We're able to divide by 2 because p is an odd prime. Okay, nice. But now there are only certain types of primes that allow minus 2 to be a perfect square. And those primes can be represented as congruent to 1 or 3 modulo 8. But now if the prime dividing this number is congruent to 1 or 3 mod 8, then that means that this number is also congruent to 1 or 3 mod 8. So here we have a squared minus a plus 1 is congruent to 1 or 3 modulo 8. And now we're going to look at this one case at a time. So let's first look at the case when this is congruent to 1 mod 8. But then we can subtract 1 from both sides, and we'll have a times a minus 1 is congruent to 0 modulo 8. But then we can make a congruence chart to find solutions to this, or really you're looking for places where a is congruent to a squared mod 8. And you'll see that the only way for that to happen is for a to be congruent to 0 or 1 modulo 8. Those are the only solutions to that quadratic congruence. But now let's plug this way back up here. So that tells us that 2 times b squared is congruent to 5 or 6 mod 8. And again, that's just by putting 0 or 1 into this equation for a, and then reducing the whole thing mod 8. But then it's impossible to have 5 mod 8 over here because 5 is not a multiple of the GCD of 2 and 8. So that means really the only possibility that's baked into this is to have this congruent to 6 mod 8. But now there's a trick where you can divide all parts of this by 2 and get a simpler congruence. And that's going to be b squared is congruent to 3 mod 4. But as we saw before, that does not have a solution. So this has no solution. So recall that that started from the choice that we had this number a squared minus a plus 1 congruent to 1 mod 8. So that gave us no solution. So that means that's impossible. And that means we really need to look at the case when that is 3 mod 8. So let's do that. Okay, so we got everything down to this last remaining case where a squared minus a plus 1 was congruent to 3 mod 8. But now let's observe that that means that a squared minus a is congruent to 2 modulo 8. But then again, we can make a chart of a and a squared mod 8, and you'll see that the only way we achieve this difference being equal to 2 is the case when a is congruent to 2 mod 8. And that's kind of the obvious case. Because if a is 2, then a squared is 4 minus 2 is 2. But needless to say, that's the only case mod 8 as well. Okay, so we've got a is congruent to 2 mod 8. Now let's plug this up here and see what we get. So if a is 2, a cubed is 8, but that'll be congruent to 0 mod 8. So we have 2b squared congruent to minus 3 mod 8. Oh, but now 3 is not a multiple of the GCD of 2 and 8, so that means that there's no solution here as well. So putting all this together, there's no solution to our original equation. Now let's look at a case when there is a solution. Okay, so now our goal is to find all integer solutions to y squared equals x cubed minus 11. So the first thing that we're going to do is move some things around. And that'll give us x cubed equals y squared plus 11. And now we're going to factor this. So you might say, well, I can't factor that. And in fact, that's true. We can't factor it over the integers, but we can factor it over an extension of the integers. So that's the trick here, is we need to work in an extension of the integers, a so-called quadratic extension. So we can factor this as y plus the square root of minus 11 and y minus the square root of minus 11. So what have we done? Well, we factored a perfect cube as the product of two numbers, and the important thing is that these two numbers are relatively prime in, well, the extension of the integers that we're working, which is z adjoined 1/2 times 1 plus the square root of minus 11. But now, if you've got a product of two relatively prime numbers equaling a perfect cube, that means that each of them individually has to be a perfect cube. So in other words, we have y plus the square root of minus 11 must be, like I said, equal to a perfect cube. and equal to a perfect cube over in this extension. So that means it must be equal to a plus b over 1/2 times 1 plus the square root of minus 11, all cubed. But now this is like kind of a chore, but what we want to do now is extract coefficients of the square root of minus 11 from both sides of this equation. Over on the left-hand side, the coefficient is 1, but then over on the right-hand side, well, the coefficient is going to be a little bit more complicated, but it's just algebra getting there. But after that extraction and then multiplying both sides by 2, we'll have the following. We'll have b times 3a squared plus 3ab minus 2b squared equals 2. So we've got this product of two integers equal to 2. But what does that mean? Well, that means that our possibility is for b to be equal to plus minus 1 or plus minus 2. That's because b is a factor of 2. Okay, but if b is equal to 1, then that means this stuff that's left over is equal to 2. If b is equal to 2, this other stuff is equal to 1. And then similar cases when b is -1 and -2. But putting this all together, we'll have a comma b must come from the following set. So 0 comma -1, that's one possibility. 1 comma -1 is another possibility. 1, 2, and -3, -2. Or sorry, -3, 2. So those are our only possibilities for values of a and b. But the values of a and b are not the numbers that we wanted. The numbers that we wanted were values of x and y. So what we do is plug these values of a and b back here, and that'll give us, a value for y, from which we can very easily get a value for x. So I won't go through all the details as it's just arithmetic, but what we'll get is xy equals 3 and then plus minus 4, or it's equal to 15 and plus minus 58. And there you have it. Those are the only integer solutions on this curve. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.